Hello and welcome back to PC Retro Programmer. Today's video is just a continuation of the previous video, which was on the topic of instructions of the 8086 and 8088 that deal with specific registers. So they don't just work with any old general purpose register or memory location, but they actually specify which registers they can operate with. So without further ado, let's just pick up the video where we left off. Now the next block of instructions that I want to look at deal with the flags. So what I'm going to do is just assemble them all into memory, and then we can see what each of them does. But before I do that, I'm actually going to assemble another instruction, which I'll just throw in here, and that is the NOOP instruction, NOP. So this does nothing at all. It just takes 3 cycles of execution time, although of course on an 8088 it's going to take 4 cycles to load anyway. And so this does absolutely nothing. Basically you can use it to pad out code, so we may as well get that out of the way. So I'm going to put all of the other ones in that deal with flags. So first of all, there's CLC, which clears the carry flag. Then there's CLD, which clears the direction flag, and CLI, which clears the interrupt flag. So these are the only 3 flags that you can actually change directly using instructions. And then there are ones for setting them. So you can set the carry flag, set the direction flag, set the interrupt flag. And there's one more which actually complements the carry. So whatever the carry is, it sets it to the other value. If it was set, it resets it. If it's 0, then it sets it to a 1. So those are the instructions for directly working with the flags. Then there's an instruction for putting the flags into the AH register, so LAHF. So basically load AH with the flags. And then you can go back the other way from the AH register to the flag register with SAHF. Now it only deals with 8 bits of the 16-bit flag register. This is a hangover from the old 8080 instruction set. We'll see what happens when we run that shortly. So let's run some of these. Let's just start off by looking at what registers we have. And so let's do the NOOP, and absolutely nothing should change since it doesn't do anything. So now we're going to clear the carry. I think unfortunately the carry is also already cleared, so we won't see anything happen here. See, it still says no carry, NC. The direction flag is one that I'll talk about a little bit later today. But this is for clearing the direction flag. So let's do that. And it didn't actually do anything at all. The direction is still up. So it would have gone to down if it had been set. And the interrupt flag is currently enabled. We have EI, enable interrupt. So let's clear that. And now it's disable interrupt, DI. So now we have their opposites, so let's set the carry and see the result, and see now it says CY for carry. Set the direction flag, so now it should go down, DN, and STI should set the interrupt flag. So the interrupt flag is for turning interrupts on and off. So basically if you clear the interrupt flag, then the interrupts won't fire. So this means that the CPU won't respond to interrupts. Now you need interrupts for things like dealing with keyboard input and a floppy drive and all sorts of different things on your machine. So you really should only turn these off in very exceptional circumstances. It will give you just a little bit more speed, and maybe you have some really timing sensitive code that you don't want to be interfered with by interrupts firing off, and so then you can clear the interrupt flag, but always remember to set it again before you exit your program, because of course nothing much is going to work without the interrupts on. And the final one here is complement the carry. It should take us from carry to no carry, as we can see. And if I ran it again, it would go back the other way. So now we come to LAHF, and as I said, this will put 8 bits of the flags into the AH register. And you can see it just says 02 now. Now basically the carry flag goes into bit 0, then you have the parity flag goes into bit 2, the auxiliary carry into bit 4, the 0 flag in bit 6, and then the sign flag in bit 7. So those are the flags that it actually loads up, and the remaining ones are just not defined. Basically it looks like it's set those to zeros. So let's push them back into the flags now. So if I run this instruction, we won't see any changes because it's just putting exactly the same things back into the flags that we just took out. But this can be used to save the flags and restore them, or at least those flags that go into that 8-bit register. The next block of instructions are some of my favourite. They're called string instructions, and it looks like there's a lot of them, but there's actually only 5 different ones, but there's a byte and a word version of each, so 8 and 16-bit versions. And these allow you to deal with memory locations. So there's a source location, and its offset is in the SI register, and a destination location, its offset is in the DI register. And basically the source location is always taken with respect to the DS segment, and the destination location is always taken with respect to the ES segment. And so these instructions allow you to deal with a memory location or even 2 different memory locations anywhere in memory. And the advantage of them is that they're only 1 byte of machine code each. Basically there are 5 different operations. You can load into either the AL or the AX register from the source location, or you can store from the AL or AX register into the destination location, or you can actually just move between 2 different memory locations, the source and destination locations, or you can compare 2 memory locations, or you can even compare a memory location with the AL or the AX register. So very powerful instructions for just 1 byte. Of course these are coded with microcode inside the CPU, so they're little programs essentially. And the great thing about these is that every time these run, they increment the source or the destination location, or both if it happens to use both. And so these instructions can be used repeatedly to deal with a bunch of consecutive memory locations. And you can even cause these to repeat. So there's a little prefix you can add called rep, and basically you put the number of repetitions that you want to do in the CX register. So for example, if you wanted to move 10 bytes from the source location to the destination location, you just put 10 in the CX register, set up your SI and DI registers, and of course your segment registers, and then do rep MOVSB, and it will just move those 10 bytes across. So rep is 1 byte of machine code, MOVSB is 1 byte of machine code. So in 2 bytes, you can move 10 bytes of memory to memory. So very powerful. Now the compare instructions wouldn't be very useful if you could just use them with rep. There are variations of rep that will actually bomb out if the 0 flag gets set or unset respectively. There are a lot of different tricks you can do with these instructions. They're very popular for demo tricks. Now there's a couple of other things you can do. You can actually change the segment register that's used for the source location using a segment override. And there's also the possibility of decrementing the offset automatically instead of incrementing it automatically after each time one of these runs. And to do that, you set the direction flag. So that's what the STD instruction is for. But these instructions are so versatile and powerful that they deserve a video of their own, so I won't say any more about them here. The next instruction is another one of my favorites, and it's another powerful 1-byte machine code instruction. It's XLAT, which I presume stands for translate. And basically it's for doing a table lookup. It assumes that the offset of your table is in the BX register. And if you want the nth entry of the table, you just put the value n in the AL register and then call XLAT. And so it'll look up the nth byte in your table and it'll put that value, whatever it is, into the AL register. So very, very powerful and used for demo scene effects. Unfortunately, I've never actually written an effect that uses XLAT, but I will get around to it one day. So the other thing with XLAT is you can change the segment. By default, it uses the data segment for the table, but you can do a segment override. For example, if you wanted to use ES instead, you would just put ES colon in front of XLAT. So that's how you do a segment override, of course. So yeah, a really interesting instruction which is again encoded in microcode in the CPU. Now there's a handful of remaining instructions which do work with registers. So I should mention briefly push and pop. So these are for pushing 16-bit registers onto the stack and popping them back off the stack. So I'll deal with the stack when we talk about functions, but basically this is a way of saving and restoring registers to a piece of memory called the stack. If you want to save and restore the flags, you can do that using push F and pop F. So these push and pop actually work with any of the general purpose registers so long as they're 16-bit, and they actually also work with the segment registers. So basically any of the 16-bit registers that you can access directly in assembly language can be pushed and popped. Now before I get on to the final instruction for this video, there's another two that I want to include here, but we'll again discuss these in more detail in a later video. So these are the LDS and LES instructions. So basically these are for loading a segment and an offset. And as the names suggest, you can load the DS segment and an offset, or you can load the ES segment and an offset. Now the offset can be put in any of the 16-bit general purpose registers. So this is basically used for loading far pointers from memory, if you know what they are. So basically that's a segment plus an offset, all with a single instruction. So very, very useful, especially given that they work directly with the segment registers, which otherwise you'd have to load via a general purpose register. So I won't say any more about that here because this is a topic for a video on segments. Now the final instruction that I want to deal with today that uses registers is a very interesting one. It's the LEA instruction, or load effective address. Now it's a bit deceptive because this actually doesn't deal with memory at all. It doesn't access memory, it only deals with addresses, and so it's really only dealing with registers and an optional offset that you specify. So basically whenever you access memory, you do that using one of the many addressing modes of the CPU, and we've already seen a few of these. For example, if I want to access something whose address is in SI, that's a possible memory addressing mode. Or I could use BX plus SI. And as I mentioned, you can also add an optional offset. So it could be BX plus SI plus 123, for example. So there are lots of these memory addressing modes on these CPUs. And whenever you specify one of these, the CPU has to do a little internal computation to figure out the offset that you're referring to. So if you had BX plus SI plus some constant, it would have to add BX, SI and that constant together, and this computation is called the effective address computation. So LEA actually just does that computation explicitly for you, and you can store the result in any register that's 16 bits and general purpose. So let's take a look at an example. Basically I'm going to do LEA, and I'm going to store the result in the AX register, but I can use any 16-bit general purpose register for that. And what memory location will I specify? Well, let's take BX plus SI, and then I can specify a 16-bit hexadecimal offset. I can actually make it negative, even with debug. It would just translate that to the corresponding 16-bit hexadecimal value. And so let's run this. Now, bear in mind, this is not going to access that memory location. All it's going to do is compute the address of that memory location. And what will its address be? Well, it will just be BX plus SI minus 192. Well, actually it's 192 in hexadecimal. We are dealing with debug after all. If you were using an assembler, that would be a decimal constant, but unfortunately debug doesn't have decimal constants. So let's run this, and first of all I'll put some interesting values in the registers. In the BX register I'm going to put 193, and then in the SI register I'll put 5, for example. And now let's actually run this, and I'll just show you the contents of the registers. So let's see what happens. And you can see that it took the 193 and added 5, so that gives me 198, then subtracts 192, and that will give me a result of 6. And then it stored that result in the AX register. So you can see it hasn't actually dealt with memory at all, it's just added up those three things. And basically this instruction can be used to add three things, or at least two registers and a constant, so long as the registers are an allowed memory addressing mode of the CPU, and of course there are only certain combinations that are allowed. So yeah, this can be used for some trickery. It's not a lot faster than just doing the additions by hand, to be honest, but it does save you perhaps in loading the machine code for the instruction. Obviously, the LEA instruction doesn't need very many bytes of machine code. It usually takes 2 bytes of machine code, unless you're using the optional constant, of course, in which case you're going to need more space to encode that. So that's all the instructions that I want to deal with in this video. But there's a few other things that I should mention. The first of these is that although all of these instructions that we've looked at here have specialized purposes for some of the registers, some of them also take a general purpose register as one of their operands. We saw that with the mul instruction, for example, and div, and LDS and LES, and obviously LEA and so on. Now these take general purpose registers, but the rule is wherever you can use a general purpose register on these CPUs, you can also use a memory location in that position. So this is worth noting. For example, I said we could push and pop 16-bit registers. Well, we can actually push and pop memory locations as well. Now, I should have also mentioned, with regard to push and pop, that they're storing that information, that register or memory location, on the stack, and the stack itself is pointed to by the stack pointer, which is the SP register. So that's a specialized purpose for the SP register, and of course all of this is inside the stack segment. So the other thing that I should mention is a handful of other instructions that are probably best dealt with in their own more detailed videos. One lot of instructions are the loop instructions, of which there are 3, loop, loop Z, and loop NZ. And basically these are designed to create loops in your code that loop for a certain number of iterations. and possibly bomb out on some other condition as well. And the number of iterations that you want them to loop for is placed in the CX register. So you can see that CX is basically used as a loop counter for a number of instructions. We saw this, for example, with the wrap instruction as well. So then there are some additional instructions that work with registers. For example, the input and output instructions. Now, this is for the CPU to communicate with the rest of the world. One way it does it is via ports, and there's two instructions, in and out, for reading from and writing to ports, which is an entire topic of its own for another video. But it's good to know at the moment that one of the versions of these port instructions can take the port number in the DX register. So that's another specialized purpose for DX. And when it's reading and writing to ports, the value that it reads in or writes out will be in the AL register, usually, if it's a byte. And if it's writing bytes to consecutive ports, so 2 bytes in a row, then it will use AL and AH. So that's again some more specialized uses for the AX register. So now let me give a bit of a summary, but with respect to registers instead of instructions. And I'll weave in some additional information from prior videos where we already saw specialized use of registers before we even got onto the register topic. So the AL and AX registers are the accumulators, 8 and 16-bit respectively, and they're really used by a lot of instructions. We saw the sign extension, those weird instructions, AAA, DAS, mul and div. Some of the string instructions would use AL or AX, depending if they were byte or word versions, and XLAT used the AL register. And we also saw some of the basic instructions were optimized for use with the accumulators. Now, there are a handful of instructions that use DX-AX as a kind of 32-bit quantity. We saw that with mul and div and sign extension. And then the BX register. Now, this is often used to hold an address, specifically a base address, the start of a table, for example, in memory. And the most common way of using it is along with one of the index registers, SI or DI. You don't have to use it with them, you can just use it on its own, but if you want to index the nth byte in a table that starts at the address in BX, you put the value n in one of the index registers. And the BP register can be used in a similar way. You could have BP plus SI or BP plus DI. And actually with all of these different addressing modes, you can also add an optional constant. We saw that above when we looked at the LEA instruction. In fact, it's still on the screen there. So, for example, you might have a header at the beginning of your table you want to skip over, and that extra constant allows you to skip over that and start your indexing somewhere else within the table. SI and DI can actually also just be used on their own, by the way, and in that case, they're taken with respect to the data segment, just like BX. But when you work with BP, it's always with respect to the stack segment unless you override it. So this is actually a feature that we've already used, but we didn't notice it at the time. So when you call a function, all of the arguments of the function are passed on the stack, and at the start of the function that's pointed to by the stack pointer. So the very first thing you do is you move the stack pointer into BP so that it gives continued access to the arguments of a function like a little table. And we didn't actually see this directly because the assembler hides it, but when you access an argument of a function, it replaces that. We do it by name. It replaces it with BP plus some constant. So it just looks up the appropriate argument within that little table. And so long as you don't mess up the BP register, it can continue to do that. And then the SP register can continue on to be used for the stack. And in fact, we tend not to use SP for much else. That's because even if an interrupt is called, you're going to be calling on the SP register because you need the stack. And same when you're calling functions and so on. So you really have to write very careful code if you want to use SP for something else. It is a general purpose register, but it tends to only be used for that one purpose, namely accessing the stack. So there was also a little bit of a weird version of BX as a base address using the XLAT instruction. So instead of the index within the table being in either SI or DI, the XLAT expects the index to be in the AL register. And I guess the reason they did that is they just wanted to keep the number of registers that were needed to use the XLAT instruction to a minimum. Just 2 registers instead of 3. Also, SI and DI had special purposes with respect to the string instructions. Remember, SI could be used as a specialized source address with respect to the data segment unless you override it, and DI as a destination address when used with string instructions, this time with respect to the ES extra segment. So those are some additional special purposes of SI and DI. Now the CX register can contain a count. So we saw this with the loop instructions and also with the rep instructions. Be a number of iterations basically. And then the CL register can actually be used to count the number of bits that you want to shift by when using the shift or rotate instructions. We already saw DX could be combined with AX with a handful of instructions, but its other purpose is to store port addresses. So these are not memory addresses, they're specialized numbering, port numbers if you like, which basically registers within peripherals and so on that you can access. It's the CPU's way of communicating with the rest of the world, or one of the ways. So we've actually covered, I think, all of the general purpose registers there. So then there are the 4 segment registers, CS obviously for code, which is where your program will typically be, SS for the stack, used for function arguments and for saving and restoring registers. DS is used for the data of your program, and ES is just an extra segment which you can put anywhere you want and use it for anything. For example, maybe the start address of video memory or something like that. So then there are the flags. This is just a single 16-bit register. Only certain bits do something, and these are basically controllable. At least the carry, direction, and interrupt flags are directly controllable using the clear, set, or complement operations that we looked at. You can also copy the flags, or at least 8 bits of the 16-bit flag register into the AH register, modify that, and then copy it back. So that gives you control over most of the flags. And these are typically used with conditional jump instructions. So this gives you some kind of control flow in your program based on various conditions. The arithmetic and logic instructions set the flags appropriately depending on certain conditions, and so you detect those with conditional jumps and jump about your program when a certain condition is met. The flag 0 also has some special uses with the rep and loop instructions, the rep NZ, rep Z, loop Z, and loop NZ. So I think that covers all of the main uses of the registers. There are probably others that I've missed, but that gives you a kind of picture of how these CPU registers are used. And as I said, we'll come back to dealing with a lot of these topics individually in more detailed videos, but there of course we'll have some really cool, fun example programs to look at.